So now that you know your 7 strong acids and your 7 strong bases, everything else is going to be a weak acid or a weak base. So if it is weak, that means it is only going to partially dissociate or ionize in solution. This includes any acids and bases that are not on the strong list of 14 that you have to memorize. So when we're talking about weak acids and bases, we have to use equilibrium properties because they don't completely dissociate. The reaction does not go all the way to the right. So we'll talk about Ka, which is going to be the acid ionization constant. So K for equilibrium, A for acid. So when you have your general formula of an acid plus water, you're going to be getting the hydronium ion and a conjugate base. So if you're to just write that in shorthand, your acid here dissociates into hydrogen ions and anions. So you can write your generic formula for your acid ionization constant. So this is just equilibrium, so you write it from equilibrium. So we do products first, so let's use this top equation because it's going to be the most complete. H3O plus conjugate base over acid concentration. Do we include water? I hope you said, Dr. B, we do not include water because water is a pure liquid, and pure liquids are not included in the ionization constant because they don't have a concentration. And you would be correct. Now, shorthand way, which is the Dr. B primary way, is going to be H plus A minus over the acid. So the broken parts, the complete part. Or, because remember, for equilibrium, you have products over reactants. Now, here when we're talking about acids and bases, the thing to remember here is you're going to have your conjugate acid and your conjugate base, because those are going to be your products, right? Over your concentration of your acid. Learn one of these. It doesn't matter to me which one. There's 3 choices. There's going to be one that you prefer. I personally prefer this one. That's from my brain. There's nothing particularly better or worse about it. So now, let's think about this. If we have a small Ka, so to get a small number, that means we have a big denominator. So if we have a big denominator, if we have a large concentration of acid at equilibrium, means there is less dissociation. So we don't have very many products. So that means it's going to be a weaker acid, because weak is relative. And then if it has a larger Ka, so that means we have more products relative to our reactant. That means we have more dissociation. So it's a relatively stronger acid, but not strong, not enough to make the list. Now with the base, it's very similar. Instead of Ka, you're going to have Kb. K for equilibrium, B for base. Now, here is where things get a little bit tricky. It's not that bad though, so don't panic. So you have your base, you put it in water, you get your conjugate acid, and then you get your hydroxide groups, which would be your conjugate base. Now, when you have a base that has more than one hydroxide group, like these 3 strong bases up here, they're a little different. They actually lose both hydroxides in one step. So that's why you have the N coefficient. So if this was like BaOH3, you would lose all three of them. If you have 2, it would be 2. So you have to include that in your equilibrium. So again, look at your balanced equation or write a balanced equation. So Kb would be your concentration of your base times your concentration of hydroxide ion. But look, there might be a coefficient here. Sometimes the coefficient is 1, but you have to pay attention to it. So this is what's different about the base. You have to pay attention to this coefficient. Acids, even whether they're strong or weak, they lose their protons one at a time over your starting concentration of your base. Because this is liquid water, it's a pure liquid, they don't have concentrations, they're left out of the equilibrium. So you can also say your conjugate acid times your conjugate base, that would be your hydroxide. Pay attention to the coefficient, it becomes the exponent, over your starting concentration of your base. Similarly, if you have a small Kb, that means you have fewer products relatively to reactants. So you have less dissociation, which makes it weaker. If it's larger, it has more dissociation. So that means it is stronger. All right, so let's check here. Which acid is going to be stronger? We have these two, and we have Ka values. So remember, the larger the number, the higher, the stronger it is. So the more dissociation you have. So both of these we can probably agree are pretty small. Now, again, make sure you can look at these coefficients here, but you want to make sure you look at the order of magnitude. So this one is the stronger one because it's larger comparatively. You can look at that and you go, Dr. B, that's actually still really small. Yes, that's the point. That is why it is a weak acid.